this tiny metal block, and this magnet might change your fridge as you know it. Oh wow, yeah, that's really cold.
The idea that eventually led to the fridges we know today first came along in 1748. That's before this guy was born.
And since then, the basic principle didn't change much, until magnets.
It's been claimed that cooling with magnets or magnetocaloric cooling uses 30% less energy than your regular fridge or air conditioner at home. That matters because as our planet gets hotter and hotter every year, the need to keep things cool is also going up.
But with this, we might keep the future energy demand for cooling at bay.
We're in the center of Germany at a company where one of the first commercial magnetic fridges is being built.
I think I've never seen so many fridges in one place. Wow!
But before we get to the new fancy innovation, let's remember what cools your classic fridge at home.
So this is what a normal compressor fridge looks like, and now we're going to see something very different.
The way they work is a bit like how we cool down by sweating. A liquid like your sweat evaporates, and that takes away heat from your body and transfers it into the surroundings. And just like that, your body or your fridge gets colder. And Magnetotherm replaced the compressor with magnets and a metal block. So their fridge looks like this.
That fridge looks a bit like a spaceship. Oh yeah, it's like a metal post that has been standing outside forever. It's really cold.
If you're like me, this magnetic cooling idea sounds pretty sci-fi, so I grabbed a Magnetotherm researcher to put it into plain English.
So on a very basic level, what is the magnetocaloric effect?
It's a material getting warm or cold if we magnetize or demagnetize it.
Ah, that sounds very simple, and that device
Will show us exactly how this feels.
The material is this metal block that sits inside this plastic pizza slice. By putting a magnet next to it, the metal block's temperature can increase by about 1 degree Celsius.
But what happens here on the atomic level? Like, why does the material heat up?
Yeah, in our magnetocalorics we have magnetic moments that can move around freely. Once we apply the magnet field, they get like aligned, and all the energy contained in the movement is expelled to the lattice. It warms up, and vice versa.
So basically the magnetic moments absorb and give away
Exactly.
energy.
We store energy in like the magnetic moments and their ordering.
And this cycle on repeat is the basis of the cooling device. The rotating magnets alternately heat up and cool down the special metal blocks, while water is piped through in a loop.
By this magnetization, the metal inside gets hot. And then we push water through this metal structure and create hot water. And then we release it into the atmosphere, like at the fridge at home. We have at the back also the heat exchanger. And then we demagnetize the material by putting the magnet away, and then this module gets colder, or the material gets colder, and then we can cool down water. And this water can then be transferred into the fridge. So by taking away the magnet, cold metal, and then we pump water through, cool down the water, and this is basically what you can touch and feel here.
By pumping the water past the metal block at the right time, you can cool it down more and more. Still, you need a few of these units working together to get the temperature down to about 9 degrees Celsius. And to really make it work, the mechanical choreography of magnetization, pumps and valves needs to be precisely timed. Based on the concept, Magnetotherm has developed two fridges, the Polaris, a barrel cooler with 85 watts, and a bigger two-door fridge with a rated power of 400 watts. So how do they compare to conventional fridges in terms of energy efficiency and pricing? We'll get to that in a minute.
Because that has a lot to do with what it actually takes to build them. First, the special magnetizable materials that heat up or cool down.
For their prototypes, Magnetotherm mainly used gadolinium because of its great magnetic properties, but it's a rare earth element and quite expensive. So the company came up with a different mix of materials that react in a similar way.
We are using an iron-based alloy with about 75–80 mass% of iron, and this is our material in powdered form, a lanthanum iron silicon-based alloy.
Yes, lanthanum is still a rare earth metal, but it only makes up 8% of the final material mix according to the company. But then there is also the challenge to get the powder into its solid rectangular form. This is done in a complex 3D printing process. After that, the structure gets hardened in an oven to reach its final form. And this is the reason for the 3D printing.
So when you look at it from a certain angle, you can see right through the entire block. It's really like a Swiss cheese, you would say.
Yeah, and that's important. We need a continuous network of channels through the material to extract the heat and cold that we produce, and that's basically the bottleneck, getting out the heat as quickly as possible and the cold.
But there's of course a limit to how big these holes can be. At some point the block would just collapse. Another tricky part of magnetic cooling is designing the cooling cycle. As you heard in the beginning, you can't operate just one of these pizza slices. You need several instead of just one compressor as in your fridge at home.
If you put your magnetocaloric material into a feeder like that, the temperature change that you get is about 5 degrees, 5 or 6 degrees. And of course, that's not enough to cool something.
This is Rasmus Björk. He has researched magnetocaloric cooling and possible applications for more than 15 years.
So you need to build up this elaborate cycle, which is called an active magnetic regeneration cycle, where you take this temperature that is smaller than the temperature span you want, and then you do something clever with the heat transfer fluid and push it back and forth, and then you can build up a larger temperature span. But it makes operations inherently more complicated.
Because of these complexities, Magnetherm say they have been running their fridges for as much as 10,000 test hours to eliminate all the errors connected to valves, pumps, fluid flow control, and so on. All of this took more than 6 years, and we haven't even talked about upscaling yet. But before we open that can of worms, let's focus on
energy savings. That's the reason we came here in the first place. And depending on who you talk to or which study you read, these fridges can be 20 to 30% more efficient than vapor compression ones.
at least technically.
So you're aiming for 30%, and where are you currently sitting at?
So if you compare system by system, it really depends on the system, because you have also components like lighting, electronics around it. So we are already comparable to existing fridges, and depending on the one, we're already better. So we have done tests in supermarkets where we are already 100% better. But generally speaking, we are aiming at 30% more.
Of course, it very much depends on if you're comparing yourself against an old cheap supermarket system versus a new optimized to the max compressor fridge. Usually fridges are measured on the Energy Efficiency Index, or EEI. It's a scale that goes from A all the way to G. Magnetherm hasn't been officially tested yet, but they expect to reach an EEI of 19 with their Eclipse model, so just making it into B. And there are commercial fridges that perform worse than that, but there are also the ones that perform better while being bigger at the same time. Another way to look at the efficiency of fridges is by measuring how much cooling you get for the amount of energy you put in. Other commercial fridges sit at a 1:3, 4 or even 6 ratio.
Where do your fridges sit on that scale?
Well, with the Polaris unit, we started around 1, but with the Eclipse unit, the new one, we start at 2. And with further improvements, we can reach 3 by the end of the year. But in the long term, 5 and more is possible.
So a work in progress to match the latest compressor fridges. A study from the Technical University of Denmark calls a magnet system with a COP of 6.2 competitive with traditional vapor compression systems, so even higher than Magnetherm's goal of 5. I've also checked with a bunch of companies that build fridges and cooling mechanisms. Some said they are not looking into this technology. Others, like GE Appliances, started research projects years ago but ended up dropping them. One said that Magnetotherm would need to achieve at least 600 watts of cooling power before they would consider using their magnetic cooling system. Better even 1000. Currently, Magnetotherm's best is 400 watts, so not enough yet.
What are the things that you're working on to increase the cooling power that you get out of such a system?
So the biggest part of the advancements are in the magnet. So we need to optimize the magnet because it's our, let's say, incoming energy that we are using in order to create the cooling. So we want to get the magnet as small and as light as possible.
And this matters because the more cooling power you want, the bigger your magnet would need to get. At the Technical University of Denmark, Rasmus and his team built a 2000 watt system. The magnets weigh around 50 kilos. Magnetotherm's theoretical maximum capacity would mean magnets 15 times bigger than this. That's a whole lot of magnets which would be needed for cooling buildings or server farms, for example.
You're always faced with the fact that you are competing against a compressor that costs €5 to build, and you can put in your fridge and just works. And it is not possible to compete with that $5 cost at the moment.
These magnet fridges cost €6,500. The bigger ones even €16,000.
Comparable conventional models cost a third of that or less. Magnetotherm say that one of their fridges would save enough energy to make up for the extra costs within 3 years. But for that, manufacturing costs would have to come down by, say, scaling up production to at least 1,000 or 2,000 units.
Magnetic cooling promises great energy savings, but as you heard today, they are still working on achieving these efficiency ratings. And for bigger stuff like server farm cooling, we need to increase sizes by 15 times or even more. And then there is still the very much relevant question about money and costs. So we might not see magnetic cooling in our personal fridges or ACs, but in fields that are willing to pay the extra money. Cooling medicine, for example. If you did like our video on magnetic fridges, please like it, comment on it and share it. And don't forget to subscribe to our channel. We got new content on environmental issues coming very soon.